This is the Xilinx UltraScale ZCU104 evaluation board, and this is the Analog Discovery 3. And as you can see here, the PMOD I2C is connected to the Analog Discovery. And in today's video, we are going to run the ZCU104 as the master device, and we are going to run the Analog Discovery as the slave device and debug the I2C protocol communication between these two nodes. I2C is a serial communication protocol based on the two wires, serial clock and serial data. It's asynchronous. Why it's asynchronous? Because the master node is sharing the clock between all the slaves that we have in the I2C network. Both clock and data lines must be pulled up to the power supply. And both master and a slave, they need to work with the open drain. What does it mean to work with the open drains? It means that their output only swap between 0 and high impedance Z. Why it's like that? Because in the I2C network, any node can be master or a slave and start to share the data with another device. So in this way, we avoid damaging to the nodes that we have in our I2C network. But open drain also limit the speed of the I2C. The standard speed is 100 kHz. In the fast mode, I2C can go up to the 400 kHz. Learning the data frame in the I2C is necessary for the debugging. So how does the master start to transfer the data toward the targeted slave? First of all, the master initiates the start bit. What is the start bit? For the start bit, the SDA change from the high to the low while the S clock is still high. So it indicates the start bit. After the start bit, the next 8 bits are the address of the targeted slave and the read-write mode. As you can see here, these 7 bits from the A0 to the A6, they are indicating the slave address, and read-write bit is telling to that slave that the master wants to read or write to that node. If the targeted slave exists on the network, it will answer by sending the acknowledge. And after that, the master starts to sending the data. As you can see here, D0 to D7 is or 1 byte of the data. The master can send multiple bytes of the data, and for each byte of the data, an acknowledge is received by the master. And at the end of the protocol, the master will send the stop bit to indicate that the communication between the master and that slave node is finished. So you can see all the steps that I explained here in this block diagram. That we have a start condition, we send the address bit and the read-write mode. After that, we receive the acknowledge. After that, we send the data, and at the end, we have the stop condition. How today we are going to experience the I2C protocol? We have a ZCU104 evaluation board, and that's a Zynq UltraScale FPGA. The Zynq UltraScale FPGA or chipset, they come with the I2C peripheral. We have a PS I2C that is connected to the ARM core. So we can configure that I2C in the Vivado environment, and later on, by the help of the Vitis, we run our application on the ARM core, and it will start to drive the I2C peripheral that we have here. The I2C peripheral that we have in the heart of our FPGA is connected to the PMOD I2C by the two MIO pins, MIO17 and MIO16. The external I2C devices, like the sensors, like the analog to digital converters, they can get connected to that PMOD I2C that we have in our evaluation boards, and then we can make the communication between the I2C peripheral and the external I2C node that we have. For example, in today's training, I'm going to use the Analog Discovery 3 for the debugging and observe all the transferred packet in the I2C network. That's really nice. It helps us to understand how does the I2C work. Usually before we connect our sensors or we connect our A to D or D to A, we first test the protocol with one of the debugging tools like the Analog Discovery 3. As you can see in this figure from the user manual, serial clock and serial data are connected to the PMOD I2C. But also the ground and power supply are also provided to that PMOD I2C. So you can share that ground to the analog discovery, or if you have any sensor here as the I2C node, and you can also connect your pull-up resistor directly to the provided power supply from that PMOD I2C. So that's what I did here between the analog discovery and my evaluation board. I connect the S clock to the DIO 0 of the analog discovery, and I connect the SDA or serial data to the DIO 1 of the analog discovery. So let's go and start our Vivado design. I already created a Vivado project for the ZCU104 evaluation board. So I open the block design and I add a Zynq UltraScale IP MPSoC IP to my design. As soon as I add the Zynq UltraScale MPSoC IP, Vivado asks me if I want to use the run block automation to configure the PS, to configure the processing system for me, and it will automatically configure all the peripherals and different sections in my ARM core. After the configuration finished, if I open my Zynq UltraScale IP, I can see that peripheral I2C1 is configured by the automatic configuration and is connected to the MIO 16 and 17. If we check the user manual of the ZCU104 board, we can see that the PS I2C1 is connected to the MIO 17 and the 16, and after the level shifter is connected to the pin header J116, and that's the P mode for our I2C communication. It allows us that the evaluation board communicate with the external I2C nodes. So that's all that we need to do to use the PS I2C communication, because I don't need the ports of the master and the slave that I have in my Zynq UltraScale. I'm going to do a quick modification for the PSPL configuration. I just need to remove the master high performance ports. Alright, we are all done, and I can add the top wrapper to my design. Since in this training we only work with the ARM processor system, and we are going to work with the I2C peripheral that is located in the processing system side, we don't need to add anything in our PL or in our FPGA fabric. So I can continue directly and generate my Vitis tree. We need to export the XSA for the programming in the Vitis IDE environment. We start to create a new application project in the Vitis, and we create a new platform by selecting the XSA. We need to have a first state bootloader, and we go to the next step. You can select between any of the ARM cores that you have here, and for example for this project I'm going to work with the ARM core 0. You can select a standalone application or FreeRTOS. I'm going to use the standalone application. And we can use the hello world as the template, then it will create all the necessary things in our project. Alright, the Vitis application is created, and now we need to replace the hello world content with the proper code to program the I2C peripheral. When you want to write the application to run one of the peripherals, the best place to look for the code is the Xilinx GitHub repository. For example, here you can find all the related example to the peripheral I2C that is connected to our processing system. You can find the pull-it master, you can find the interrupted master, you can find how you can program your I2C in the slave mode, you can find the example that how you can read and write in the EEPROM. And for this tutorial, I'm going to use the I2C PS in the pull-it mode. So we copy the entire code, and then we replace the content of the hello world example with what we copy from the Xilinx GitHub repository. Before I run the code on the ARM core, it's a good idea to review the code that we just grabbed from the Xilinx GitHub repository. For example, here you can see the slave address. So in this line, we can set the targeted slave address. Here we can set the clock rate. For example, again here, the clock rate is adjusted to the 100 kilohertz. In the next section, we first configure the I2C peripherals by the help of the lookup config function and by the help of the initialize function. So in any case that you want to use any peripherals, always you will see the lookup config and initialize function. After that, in the code we will do the self-test to ensure that the hardware is configured correctly. In this line, the code is configuring the I2C clock based on what did we select before. The I2C send the data that we saved them inside a buffer. So before we send that buffer, you are going to save a known data from the 0 to the n to our buffer. After that, the I2C peripheral start to send the send buffer toward the selected I2C slave node, and after that it will read back the data from that slave node, and at the end it will compare the send and the received data, and if the data are completely equal, then it will say that our test is passed successfully. So briefly, first we configure the I2C device, we fill the send buffer with the known data, we send the data toward the slave node, and we read back the data from the slave node, and at the end we compare what did we send and what did we receive from the slave node. If they are equal, then the application will say that the test is passed successfully. Alright, for debugging we need to open the waveform to run the Analog Discovery tree, and we want to set up our Analog Discovery tree as the slave mode. So we go to the protocol window, we select the I2C protocol, and we configure Analog Discovery as the spy or the slave. Here we can also filter that the Analog Discovery only spy which address. So we set the address in the Vitis to the 55 hexadecimal, and here we will set the same value. Now I can go and run the application on the ARM cores and observe here that if I'm receiving the data that I expect or not. I want to do a last coordination between the Vitis application and the waveforms that is supposed to run the Analog Discovery tree. Here I'm going to send 10 data from the ZCU104 to the Analog Discovery. And here the Analog Discovery also will send from the 0 to 9 10 bytes from the slave to our master, that is the I2C that we are going to run on the evaluation board. So if you want to see that the test successfully run on the target, we should be so careful what data a slave is sending back to our board. Here the buffer is instantiated from the 0 to 9, and here we are going to send back the same data. Then the test will pass successfully. A bit more about the coordination is that we should set up the same clock frequency in the Analog Discovery's configuration window at the same clock that we set up in the Vitis application. And please also take care of the slave address that you set here and the slave address that you set here, that the Analog Discovery is supposed to listen to that. Alright, I'm ready to run my code on the evaluation. Alright, we can see that they successfully run the I2C master pulled example test. What happened in the log of the Analog Discovery? We can see that we received from the 0, 1, 2, 3, 4 to the 9. The master sent the start bit. It's exactly what I was explaining here for you guys. The master sent the start bit, and then it sent the address and the read write, and then it sent the data, and we will have a stop. So let's look at that here. We have a start bit, we have an address plus write mode. We have an address of the 55 that is sent from the evaluation board, and the master is indicating the write mode, and then it sends our data, and after that we have a stop bit, exactly match to this block diagram. And in the second time, the master send the start bit, and this time is telling to the address H55 that I want to read from the slave node with the address H55. This time the slave sends from the 0 to the 9 the data that we set here. And here in the Vitis console we can see that when the application compares the sent data with the received data, they completely match and fit to each other, and we pass the test successfully. Analog Discovery 3 also can work as the logic analyzer and show the log of our data in a very nice mode. So I go and I open the logic and I select to work with the protocol I2C, and then I select the DI0 and the DI1 as the serial clock and the serial data, and this time I want to run my code again on the ARM core. As soon as the data transmission is started, the trigger is activated. I could see the data is logged here. So what we can see here, yeah, it's very nice. It's really nice. We can see the serial clock. We can see the serial clock with the frequency of the 100 Hz. We can see again that the master instantiates the start bit. It sends the address of the slave. And at the first, it decided to write to the slave. It's the address plus the write mode, and then it received the acknowledge, and after that it starts to send the data, and after sending the each byte it also receiving the acknowledge. So H00, H01, 02, and all the 10 data is received, and at the end the stop bit is also sent from the master. In the next transaction, as you can see here, again the master initiates the start bit, it sends the address, and this time the mode is the read mode. As the final test, I just modify the code a little bit to write into my slave 5 times. As you can see here, I added the for loop. And inside the for loop, I'm sending to the slave the send buffer 5 times, and in the next for loop 5 times I'm also reading back the data from the slave. I want to ensure that the protocol is robust enough and is working without any error. And also I show the received data from the slave in the last section of the code to see what data we are receiving from the slave. So let's run this code and see the result. Alright, we can see 5 successful write here. We can also track them here in the console of the waveform. We can see 5 successful write, and the data also is what we expected from 0 to 9. And we also have 5 successful read from our slave. And at the end, you can also see that the read data from the slave is 0 to the 9, and that's what we write here. Here we write from the 0 to the 9. So it shows that the setup and the application and I2C peripheral is working functional without any bug or error. You can also here observe that I'm using the I2C PMOD and power supply, shared ground, S-clock, and STA. And you can also see the pull-up resistors that they are pulling the S-clock and STA.